Hi viewers, welcome to my channel. In the present class now I am going to discuss the topic the derivations of the Kepler's second and third law. First let us see the statements of Kepler's second and third law. The areal velocity of radius vector of your planet remains constant, or the radius vector of your planet in an elliptical orbit sweeps out equal areas in equal intervals of time. The third Kepler's third law, the statement is the square of the time period of revolution of your planet is directly proportional to the cube of semi-major axis. That we represented as t square is directly proportional to a cube, where t is the time period, a semi-major axis. So let us derive these Kepler's second and third law. So for that, consider this figure. This is the radius vector. Sun existing at this focus. At any instant of time, the planet is at the position P. In the time interval delta T, the planet reached to the position P dash. There the displacement delta R bar. Here angle is delta theta. The radius vector at the position P R bar at the P dash R bar plus delta R bar. Okay. So what is the first law? Planets revolve around the sun in the elliptical orbit. Yes. Now, at any instant of time, the planet is at the position P. In the short time interval delta t, it is changed to the position P dash. Then the radius vector change from R bar to R bar plus delta R bar. Then the arc delta R bar PP dash subtends angle delta theta at the center. Yes. Okay. Now, the area swept by the radius vector in the time interval delta t, let us write the area swept by the radius vector swept by the radius vector in the short time interval delta t, is given by delta a. Delta a is equal to half into r square delta theta. How we are writing? That is the area of sector SP P dash. Area of SP P dash. Okay. So this is the area swept by the radius vector in the time interval delta t. So that area is given by delta A equal to half r square delta t. Okay. That is the area of SP P dash sector half into r delta theta. అట్లా రాస్తున్నాము అంటే PP dash is equal to delta R, that equal to R delta theta. area delta A is equal to, using the formula of into base into height, R into R delta theta equal to half R square delta theta. Yes. Now, dividing with the delta T both sides, delta A by delta T equal to half R square delta theta by delta T. Okay, right. So here the time interval is very short. Therefore, when you apply the limit, delta t tends to 0, delta A by delta t is equal to half R square limit delta t tends to 0, delta theta by delta t. Then the left hand side we can write it as dA by dt is equal to half R square. This is d theta by dt. Okay. But d theta by dt is equal to omega, angular velocity. Hence, dA by dt is equal to half R square. It is omega. Since omega equals to d theta by dt. Okay. So multiplying with m in numerator and denominator, then we get mr square omega by m. But mr square omega is angular momentum, then by 2. So there we have taken the substitution L is equal to mr square omega. Yes. So finally we got dA by dt equal to L by 2m, where L is the angular momentum, m is the mass of the planet. But the angular momentum remains constant under the central force. Okay. So already we proved. Therefore, dA by dt equal to constant. That means the areal velocity of radius vector always remains constant. That means the area swept by the radius vector in equal intervals of time sweeps out equal areas. The radius vector sweeps out equal areas in the equal intervals of time, or we can say it in another words, simply the aerial velocity, the radius vector, aerial velocity always remains constant. Okay. Next, Kepler's third law. So for that, we consider again this figure. This is the ellipse. This is major axis. This one minor axis. So here the sun existing in any one of the 40. Yes, is here. Semi-major axis I am denoting with the small e. Semi-minor axis denoting with the small b. Okay. Now the radius vector. This is the radius vector. Here is the planet. Yes. The time taken to complete one revolution is nothing but time period. The square of the time period is directly proportional to cube of the semi-major axis. This is the Kepler's theorem. And also we can write it as t directly proportional to a power 3 by 2. Okay. Right. Here, we can say this statement in other words that the square of the time period is directly proportional to cube of the main distance between the sun and the planet, t square proportional to r cube. Here r is equal to a. The main distance between sun and planet almost equal to the semi-major axis. That's why the statement we are writing like this: T square directly proportional to AQ. Now, let us see the proof. Yes, again I'm writing T square is directly proportional to AQ. So this we should prove. Yes. Now time period of the revolution of planet is defined as T is equal to area swept by radius vector in one revolution followed by aerial velocity. Aerial velocity. The area, the total area swept by the radius vector one rotation, how much? That equals to pi AB, area of ellipse, where A major axis, B minor axis, by aerial velocity dA by dt. This is equation 1. Okay, but we proved that dA by dt is equal to h by 2, where aerial velocity constant, where h is equal to L by smaller angular momentum per unit mass, or mr square omega, r square d theta by dt. Yes. So substituting this h by 2 in equation 1, then we get t is equal to pi ab by h by 2 equals to 2 pi ab by h, equation 2. Okay. But from conic section, semi-lattice rectum, L is equal to h square by mu. From this, h is equal to root of mu L. So substituting that in the equation 2, t is equal to 2 pi ab by h, that equals to 2 pi ab by h is root mu L, equation 3. And also semi-lattice rectum L is equal to b square by a. So in equation 3, I am converting L in terms of semi-major and minor axis. From this, b square is equal to a, b equal to root a, b equal to 2pl. Of course, it is not required, right? Then substituting that, t is equal to 2 pi ab by root mu into L is b square by a, equals to, yes, root b square and b cancel this one, then 2 pi a power 3 by 2 by root mu. Okay, root mu. Where what is mu? Mu is equal to capital Z capital. Hence, T is equal to 2 pi by root Gm capital G capital M a power 3 by 2. Okay, square in both sides. T square is equal to 4 pi square by g m a q, where capital G universal gravitational constant, m mass of the sun, a semi-major axis, t time period of revolution. So from this, we can relate the time period and semi-major axis as p square is directly proportional to aq, since g and m are constant. Therefore, the square of the time period is directly proportional to the semi-major axis. Okay, so Kepler's second law, what we are saying, the aerial velocity of radius vector, the means constant, or the radius vector of the planet, the sweeps of equal areas in equal intervals of time, dA by dt equal constant. Kepler's third law states that p square directly proportional to aq, that is, the square of the time period of revolution of the planet is directly proportional to cube of the semi-major axis.